Hey everyone, and welcome to Airwise Academy, your trusted source for ESA Part 66 learning. Today, we will continue our journey with Module 2, Physics, and specifically to our second submodule, Mechanics. This submodule covers the fundamental principles governing the behavior of objects and fluids. We'll be diving into four key areas: statics, kinetics, dynamics, and fluid dynamics. Let's take a closer look. As you can see, the four sections of mechanics are statics, kinetics, dynamics, and fluid dynamics. First, we have statics. This is where we study objects that are at rest or in a state of balance. We'll be looking at forces, moments, and the concepts of stress, strain, and center of gravity. Next, we'll move into kinetics, which is the study of motion itself. We'll analyze how things move, whether in a straight line, in a circle, or in a periodic motion like a pendulum. After that, we'll cover dynamics, where we connect motion to its causes. This is where we bring in foundational principles like force, mass, energy, momentum, and friction. And finally, we'll wrap up with fluid dynamics, which is absolutely essential in aviation. We'll explore how fluids, both liquids and gases, behave, covering everything from viscosity to the famous Bernoulli's theorem, which is key to understanding how wings generate lift. This structure will guide us through the next four lessons. In this video, we will explore the very first section on that list, statics. Now, let's dive into the first section, statics, the study of forces acting on stationary objects. Understanding statics is crucial in aviation, whether analyzing load distribution on an aircraft wing or calculating the buoyancy of a fuel tank. Today, we'll explore core concepts like forces represented as vectors, the center of gravity's role in stability, and how materials behave under stress. We'll also discuss fluid pressure principles that apply to instruments like barometers. By the end, you'll see how these principles ensure safe and efficient aircraft design. For B1 licensed engineers, the required knowledge level for statics is level 2. This means you are expected to have a deeper understanding, be able to explain system functions, and understand how components work together. You'll carry out maintenance tasks, often with technical guidance or reference to manuals. For B2 licensed engineers, the required knowledge level for statics is level 1. At this level, you need a general awareness and basic knowledge. You'll be able to perform simple procedures, but always under supervision. Now, let's get started. A force is any influence that changes an object's motion or causes stress in a stationary body. For a moving object, we calculate force using mass times acceleration. For a stationary structure, force induces stress, measured in newtons or pounds. If a force is applied away from a pivot, we account for distance, e.g., pound-inches. Forces are vectors. Arrows show direction, while length indicates strength. In aerodynamics, vectors combine to determine lift. In weight balancing, they help locate the center of gravity. If two equal forces push, pull in exact opposite directions at the same point, they cancel out. But if they're parallel and offset, like two hands turning a wrench, they form a couple, producing rotation, torque. The moment is the lever arm distance from force to pivot. Unlike moments, torque from couples is a free vector. Its effect doesn't depend on a specific reference point. The center of gravity, or CG, is a fundamental concept in aviation. It's the balance point where a body or an aircraft remains stable without tilting. To quantify this, we use two key terms: arm, which is the horizontal distance from a fixed reference called the datum, and moment, the product of weight and arm. Why does this matter? For maintenance crews, CG stability ensures safe modifications, while pilots must calculate it when loading cargo or fuel. Precise calculations keep the CG within safe limits, which we'll explore further in Module 07A. When an aircraft is in flight, its structure battles external forces like air resistance or engine thrust by generating internal resistance. This resistance, called stress, prevents deformation. Engineers identify 5 major types of stress that all aircraft are subjected to. These are tension, compression, torsion, shear, and bending. We'll explore each of these in detail, understanding how they manifest and what they mean for aircraft design and safety. First up is tension. This is the stress that directly resists a force attempting to pull an object apart. Think of a tug of war. In an aircraft, a classic example is the engine pulling the aircraft forward while air resistance simultaneously tries to hold it back. This creates a powerful tensile force that effectively tries to stretch the aircraft. The material's ability to resist this pulling force is known as its tensile strength, which is measured in pounds per square inch, or PSI. It's calculated by dividing the load required to pull the material apart by its cross-sectional area. Conversely, compression is the stress that resists a crushing force. When a plane lands, the landing gear compresses to absorb impact. If the load exceeds the material's compressive strength, it buckles. Like tensile strength, a material's compressive strength is also measured in pounds per square inch, indicating its ability to withstand being squeezed. Next, we have torsion, which is the stress that resists twisting. When an aircraft engine generates thrust to move the aircraft forward, it can also induce a twisting motion. While the engine might try to twist the airframe to one side, other components are designed to hold the aircraft on its intended course, thereby creating torsional stress. The torsion strength of a material is its capacity to resist this twisting or torque. Shear stress is encountered when one layer of a material tries to slide over an adjacent layer. Rivets in wings face shear stress, like scissors cutting paper. If shear forces overpower the rivets, layers slide apart, risking structural failure. This type of stress is particularly important for fastening elements like screws, bolts, and, as mentioned, rivets, which are frequently under shearing forces. Finally, we come to bending stress, which is unique because it's a combination of both compression and tension. When an object bends, one side experiences a shortening effect, putting it under compression, while the opposite side experiences a stretching effect, putting it under tension. Imagine a simple rod being bent. The material on the inside curve is compressed, while the material on the outside curve is in tension. Bending stress is particularly critical and observable in aircraft wings. Consider an airplane in flight. The aerodynamic lift tries to bend the wing upwards. This causes the skin on the top surface of the wing to be compressed, while the skin on the bottom surface is put under tension. Now, when the airplane is on the ground, sitting on its landing gear, gravity acts inversely. It tries to bend the wing downward, causing the bottom skin to be compressed and the top skin to be in tension. This alternating stress is why aircraft wings are robustly designed and undergo rigorous certification testing, where manufacturers intentionally bend the wings up and down to extreme limits to confirm they can withstand such forces without failure. Now let's explore the concept of strain. When an object experiences enough stress, it changes shape or becomes distorted. This distortion is what we call strain. Remember that matter tends to be elastic, meaning it tries to return to its original shape when the force causing the distortion is removed. Strain gauges, commonly used in turbine engine test cells, measure engine thrust by precisely quantifying how much the gauge itself is distorted by the engine's force. Similarly, a deflecting beam torque wrench measures torque by sensing the distortion of the beam. As you can see in the figure, the amount the beam deflects indicates the torque applied. Let's begin by examining the three primary states of matter: solid, liquid, and gas. Solids maintain a definite shape and volume due to their tightly packed molecules. Liquids, while maintaining a definite volume, conform to the shape of their container. Their molecules possess more energy and movement compared to solids and exhibit surface tension. Gases, in contrast, expand to fill any available space, are compressible, and their molecules possess even greater energy and freedom of movement. During a state change, such as melting or boiling, energy is either absorbed or released without a change in temperature. This is known as latent heat. The temperature remains constant as the energy is utilized for the phase transition. The boiling point, the temperature at which a liquid becomes a vapor, and vice versa, is directly related to pressure. As pressure increases, so does the boiling point, and vice versa. Refer to this figure for a visual representation of this relationship in water. Vapor pressure is the pressure exerted by the vapor that exists above a liquid within a closed container at a particular temperature. This pressure is unique to each substance. Substances with low boiling points are considered volatile as they readily develop high vapor pressure even at standard temperatures. It's important to note that vapor pressure increases with temperature. Now let's explore a fascinating concept in physics: pressure and buoyancy. What is buoyancy? Simply put, it's an upward force exerted by any fluid, whether it's a liquid like water or a gas like air, on an object submerged within it. This force has a noticeable effect. It makes objects feel lighter. If this upward buoyant force is strong enough, it can even cause an object to float. You might have experienced this yourself. Even objects denser than water, which readily sink, feel significantly lighter when submerged. This is why a person can lift much heavier weights underwater than they ever could in the air. To truly understand buoyancy, let's look at a classic experiment illustrated here in this figure. Imagine we have an overflow can filled to the brim with water and a catch bucket ready to collect any overflow. First, we weigh a heavy metal cube in still air, and let's say it weighs 10 pounds. Then, we carefully lower the cube into the water until it's completely submerged. While submerged, we weigh it again, and this time it only weighs 3 pounds. The difference between these two weights, 7 pounds, is the buoyant force exerted by the water on the cube. As the cube was lowered, water flowed out of the spout and into our catch bucket. The volume of this overflowed water is exactly equal to the volume of the cube itself. And here's the crucial part. If you were to weigh that collected water, you would find it also weighs exactly 7 pounds. This experiment beautifully demonstrates the core principle of buoyancy. Now, let's discuss Archimedes' principle. This exact observation was made by the ancient Greek mathematician and scientist Archimedes over 2 millennia ago. His findings led to what we now call Archimedes' principle. This principle states that the buoyant force which a fluid exerts upon a submerged body is equal to the weight of the fluid the body displaces. It's a fundamental concept that applies to all fluids, not just liquids. Just as water exerts an upward force on a boat, air also exerts a buoyant force on objects within it, like a hot air balloon or an airplane. So, how do we quantify this buoyant force? We use a simple formula. Buoyant force equals the volume of the object multiplied by the density of the fluid displaced. This formula helps us predict whether an object will float or sink. If the calculated buoyant force is greater than the object's weight, the object will float. If the buoyant force is less than the object's weight, it will sink. For objects that do sink, their apparent weight when submerged will be reduced by the weight of the fluid they displaced, which, remember, is the buoyant force. Let's put this into practice with an example. Imagine we have a 10 cubic foot object that weighs 700 pounds, and we place it in pure water. First, we need the density of pure water, which is approximately 62.4 pounds per cubic foot. Now, let's calculate the buoyant force. Volume of object, 10 feet, multiplied by the density of water, 62.4 pounds per cubic foot, gives us 624 pounds of buoyant force. Now, let's compare. The object weighs 700 pounds, but the buoyant force is only 624 pounds. Since the buoyant force is less than the object's weight, this object will sink. But when it's submerged, it won't feel like 700 pounds. Its measurable weight underwater will be its original weight minus the buoyant force. So, 700 minus 624, which equals 76 pounds. Buoyancy isn't just a theoretical concept. It's vital in engineering and everyday life. 2 excellent examples are helium-filled airships and seaplanes. Both use buoyancy to float, one in the air, the other on water. Let's look at the de Havilland Twin Otter seaplane, shown in the figure. This aircraft has a gross takeoff weight of 12,500 pounds. For it to float, its pontoons or floats must be large enough to displace a weight of water equal to the airplane's weight. Interestingly, current certification standards actually require these floats to be 80% larger than the absolute minimum needed to provide extra stability and safety. Let's break down the seaplane float calculation for the Twin Otter. With a weight of 12,500 pounds and knowing water's density is 62.4 pounds per cubic foot, the minimum volume of water the floats must displace is 12,500 divided by 62.4, which is 200.3 cubic feet. Now, because of the 80% certification requirement, we need to add an additional volume, 80% of 200.3 cubic feet, which comes out to 160.2 cubic feet. So the total required volume for the floats is the minimum 200.3 plus the additional 160.2, totaling 360.5 cubic feet. If you look at the Twin Otter in the picture, you can clearly see that a significant portion of the float's volume is out of the water, precisely because they are designed to be much larger than the bare minimum. Moving to the skies, airships like the large Goodyear models, shown in the figure, are another fantastic example of buoyancy. Here, the fluid they are submerged in is air. A Goodyear airship, for instance, might have a volume of 230,000 cubic feet. To calculate its buoyant force, we multiply its volume by the density of air, which is approximately 0.0761 pounds per cubic foot. This gives us a buoyant force of around 17,597 pounds. This upward force allows the airship to stay aloft. Now let's look inside an airship, specifically at components called ballonets, marked as items 1 and 2 in the figure. These are internal air chambers. Airships have a clever way to control their buoyancy. Through an air scoop, air can be pumped into these ballonets, which increases the airship's overall weight and reduces its lift. Conversely, air can be evacuated from the ballonets, decreasing its weight and increasing its lift. This precise control over weight allows pilots to manage how much positive or negative lift the airship has. While airships are classified as lighter than air aircraft, they are actually often flown in a condition that is slightly heavier than air to provide better control, especially when landing or maneuvering. Now, we'll be discussing the fundamental principles of fluid pressure. Let's start with the basics of static pressure. The key principle to understand is that the pressure a liquid exerts on the bottom of its container is determined by the height of the liquid column, not by the container's shape or the total volume of liquid it holds. This can be seen in the figure. Here we have 3 containers of different shapes and sizes, but because they are all filled with water to a height of 231 inches, the pressure at the bottom of each is exactly the same. 8.34 pounds per square inch, or PSI. So, where does that number, 8.34 PSI, come from? It's a direct calculation of force over area. If we look back at the container on the left, it had a base of 1 square inch and is filled to a height of 231 inches. This gives it a volume of 231 cubic inches, which is precisely 1 gallon. Since 1 gallon of water weighs 8.34 pounds, that weight is exerted over 1 square inch, resulting in a pressure of 8.34 psi. This also shows that pressure is adjustable by varying the fluid height. If you were to measure the pressure halfway down the column, it would be exactly half, or 4.17 psi. The pressure we've been discussing, based on the height of a fluid column, is known as static pressure. In some applications, like with gasoline feeding a carburetor, it's referred to as a head of pressure. You can create the required fuel pressure simply by positioning the tank a specific height above the carburetor. However, when a fluid is in motion, it has another type of pressure associated with its velocity, known as ram pressure. When you add this ram pressure to the static pressure, you get what is called total pressure. This measurement is critical in aviation, for example, in the inlet of a jet engine, where total pressure provides important data to the fuel metering device and cockpit instruments. This same principle of pressure caused by a column of fluid applies directly to the air around us. The Earth's atmosphere is a fluid, and it has weight. This weight creates atmospheric pressure. On a standard day at sea level, if you could take a column of air that is 1 square inch at its base and extends all the way to the top of the atmosphere, it would weigh 14.7 pounds. This is why we define standard atmospheric pressure as 14.7 psi. Naturally, as you increase in altitude, there is less air above you, so the weight of that column decreases, and so does the atmospheric pressure. So how do we measure this atmospheric pressure? One classic instrument is the mercury barometer. It works by balancing the weight of the atmosphere against the weight of a column of mercury. As you see illustrated here, atmospheric pressure pushes down on the open dish of mercury, which in turn holds up the column of mercury inside the inverted tube. Gravity tries to pull the column down. The height of the mercury stabilizes when these two forces are equal. Under standard conditions at sea level, the 14.7 psi of atmospheric pressure can support a column of mercury that is 29.92 inches tall. This is why 14.7 psi is equivalent to 29.92 inches of mercury, written as Hg. While effective, a mercury barometer isn't very practical for use on an airplane. For that, we use an aneroid barometer. This is a mechanical device that uses a sealed, flexible metal capsule. As the external atmospheric pressure changes, the capsule either expands or gets compressed. This physical movement is then amplified by a system of levers and gears to move a pointer on a dial. The most common application of the aneroid barometer in aviation is the altimeter. An altimeter is simply a very sensitive aneroid barometer, but instead of being calibrated to show pressure, it's calibrated to show altitude in thousands of feet. Since we know that atmospheric pressure decreases in a predictable way as altitude increases, the instrument can translate a pressure reading directly into an altitude. For example, standard pressure at 10,000 feet is 10.10 psi. When the altimeter's aneroid cell senses this pressure, its pointer is mechanically driven to indicate 10,000 feet on the dial. And that brings us to the end of this session for today. Now, let's warm up with a few questions to review what we've learned. Now let's get started with question 1. A force of 100 Newton is applied to a rigid body at a distance of 5 meters from a reference point. What is the moment of this force about the reference point? A. 500 Newton meters. B. 750 Newton meters. C. 1000 Newton meters. The correct answer is A. 500 Newton meters. To calculate the moment of a force, we use the formula moment equals force times distance. In this case, the force is 100 newtons and the distance is 5 meters. So, the moment is moment equals 100 newtons times 5 meters equals 500 Newton meters. Question 2. Two equal forces of 50 Newton each are applied to a rigid body, one in the positive x direction and the other in the negative x direction. What is the net force acting on the body? A. 100 Newton in the positive x direction. B. 100 Newton in the negative x direction. C. No net force. The correct answer is C. No net force. When two equal forces act on a rigid body, but in opposite directions, they cancel each other out. In this case, the 50 Newton force in the positive x direction and the 50 Newton force in the negative x direction combine to produce no net force acting on the body. This is because the forces are equal in magnitude and opposite in direction. Question 3. What is the fundamental definition of stress in a material? A. The external force applied to an airframe. B. The internal resistance of a material to deformation. C. The aerodynamic force that causes drag. The correct answer is B. The internal resistance of a material to deformation. While external forces are what cause stress, the text defines stress itself as the reaction inside the material. It says, reactionary force inside the materials of the components counter the external forces. This internal resistance to deformation is known as stress. So, stress is how the material fights back against being bent, stretched, or crushed. Question 4. When two metal plates are held together by rivets, what type of stress are the rivets primarily designed to resist? A. Torsion. B. Tension. C. Shear. The correct answer is C. Shear. If you remember, we mentioned the stress that resists the force tending to cause one layer of a material to slide over an adjacent layer. The force on the plates tries to slide them past each other, which would cut or shear the rivets. This is why the shear strength of bolts and rivets is so critical in aircraft construction. Question 5. An aircraft wing in flight experiences bending due to aerodynamic lift. This bending stress is a combination of which two other stresses? A. Shear and torsion. B. Tension and compression. C. Torsion and compression. The correct answer is B. Tension and compression. If you remember, bending stress is a combination of compression and tension. It then explains that when a wing bends upwards due to lift, the skin on top of the wing is squeezed together. That's compression, while the skin on the bottom of the wing is stretched apart, which is tension. Understanding this combination is fundamental to designing strong yet flexible aircraft wings. Question 6. What is the primary function of strain gauges in turbine engine test cells? A. To measure the thrust of the engine. B. To measure temperature changes. C. To measure fuel consumption. The correct answer is A. To measure the thrust of the engine. Strain gauges work by measuring the distortion caused by the thrust on the engine. When the engine produces thrust, it applies a force that causes the strain gauges to deform. This deformation is then quantified and translated into a thrust reading. Question 7. According to Archimedes' principle, what is the buoyant force a fluid exerts upon a submerged body equal to? A. The total volume of the submerged body. B. The weight of the fluid the body displaces. C. The density of the submerged body. Archimedes' principle is a fundamental concept in fluid mechanics. As you remember, Archimedes discovered that the buoyant force which a fluid exerts upon a submerged body is equal to the weight of the fluid the body displaces. This principle applies to all fluids, whether liquid or gas, and is key to understanding why objects float or sink. The other options, while related to the object or fluid, do not define the buoyant force itself according to Archimedes' discovery. So, the correct answer is B. The weight of the fluid the body displaces. Question 8. What condition determines if an object will float in a fluid? A. If the object's volume is less than the fluid's volume. B. If the buoyant force is less than the object's weight. C. If the buoyant force is more than the object weighs. If you remember, if the buoyant force is more than the object weighs, the object will float. Conversely, if the buoyant force is less than the object weighs, the object will sink. This highlights the direct comparison between the upward buoyant force and the downward force of the object's weight in determining its behavior in a fluid. So, the correct answer is C, if the buoyant force is more than the object weighs. Question 9. A 10-foot cubed object weighing 700 pounds is placed in pure water. Density equals 62.4 pounds per foot cubed. What is its measurable weight when completely submerged? A. 624 pounds. B. 76 pounds. C. 700 pounds. Let's break down this calculation as shown in this example. First, we calculate the buoyant force using the formula buoyant force equals volume of object times density of fluid displaced. So, buoyant force equals 10 feet cubed times 62.4 pounds per foot cubed equals 624 pounds. Since the buoyant force, 624 pounds, is less than the object's weight, 700 pounds, the object will sink. When an object sinks, its measurable weight in the submerged condition is the difference between its actual weight and the buoyant force acting on it. Measurable weight equals object's weight minus buoyant force. Measurable weight equals 700 pounds minus 624 pounds equals 76 pounds. Therefore, the object appears to weigh 76 pounds when submerged. So, the correct answer is B, 76 pounds. Question 10. How does an airship primarily control its weight and lift to enable flight? A. By changing the composition of the lifting gas, helium. B. By adjusting the amount of air in internal ballonets. C. By rapidly expelling helium from the main envelope. If you remember, we explained the mechanism unique to airships like the Goodyear models. It states, the ballonets are air chambers within the airship. Through the air scoop, air can be pumped into the ballonets or evacuated from the ballonets in order to control the weight of the airship. This adjustment of air in the ballonets allows for precise control of the airship's overall weight, thereby controlling its positive or negative lift and enabling it to be flown in a condition slightly heavier than air. So, the correct answer is B, by adjusting the amount of air in internal ballonets. Question 11. 3 containers of different shapes are filled with water to the same height. What does this demonstrate about the pressure at the bottom of each container? A. The pressure will be the same in all 3 containers. B. The container with the largest volume will have the highest pressure. C. The container with the smallest surface area will have the highest pressure. The correct answer is A. The pressure will be the same in all 3 containers. If you remember, the pressure exerted on the bottom of a container by a liquid is determined by the height of the liquid and not by the shape of the container. In the example given, even though the containers have different shapes and hold different volumes of water, they all have the same liquid height, and therefore all exert the same pressure on the bottom. This is a key principle of static pressure or head of pressure. Question 12. How does an airplane's altimeter, which is an aneroid barometer, indicate altitude? A. By measuring the weight of a mercury column inside the instrument. B. By measuring atmospheric pressure and displaying a corresponding altitude in feet. C. By adding ram pressure and static pressure to calculate a total pressure altitude. The correct answer is B. By measuring atmospheric pressure and displaying a corresponding altitude in feet. An altimeter works by measuring atmospheric pressure and showing that measurement as an altitude. If you remember, we mentioned an aneroid barometer is a mechanical instrument used as an altimeter on airplanes. We also mentioned the pressure of the atmosphere is exerted against a thin metal aneroid connected to the pointer. Critically, calibrations are made in thousands of feet rather than in psi or inches of mercury. It says that when the instrument measures a pressure of 10.10 psi, it is calibrated to point to 10,000 feet. That's all for today's lesson. If you found this video helpful, please give it a thumbs up and consider subscribing to Airwise Academy for more aviation knowledge. We'd love to hear your thoughts or questions in the comments below. Turn on notifications so you won't miss our upcoming videos. Until next time, blue skies and happy learning!